Swayam Prabha. Digital India. Educated India.
Okay, I guess that we can begin. Okay, perfect. So today we're going to talk a little bit about the fundamentals of Raman spectroscopy, because out of all the spectroscopic techniques we are dealing with, it is one of the most versatile, and to me is my main first approach technique. And I believe this is important. It also has some details and technicalities that make it special. Of course, in this handbook we go through all the techniques in very much detail, but where I want to go is into the Raman spectroscopy. And the typical Raman spectrometer is like that. Things are even changing, but before getting into how a Raman system looks like today, I want to go into how it was discovered and how it works and what makes Raman special compared to other techniques. Because you already know that Raman is reporting vibrational transitions, and the energy of vibrational transitions is associated with the wavelength of infrared radiation. But you typically make Raman with visible radiation or even ultraviolet radiation, or eventually also with infrared radiation. So how does it work? And that is what makes Raman special. So here you have not a Raman spectrometer, you have Raman's spectrometer. This is his spectrometer, which is in the campus in the Foundation of Science in Calcutta. And basically what Raman said already during the Nobel Award ceremony that he got because of this, that the character of the scattered radiation enabled us to obtain an insight in the ultimate structure of the scattering substance. And that is very true, probably even more than what he originally thought, because we can really get a major insight about what is happening in these materials that we are characterizing by the technique that has his name. So you know that in the beginning there was light, then there was matter, and then there was spectroscopy. Of course, this is an oversimplification, because from the light and the molecule to the spectrum, you need something here. You need spectrometers, you need illumination, signal collection, whatever. But conceptually, in the end, this is what is happening, that there is an interaction. Someone has the audio on, so it's better to put it mute. Good. And basically, the idea is very simple. What happens when a photon hits a molecule or a particle or something? It hits the particle and bounces out. Typically, and in most of the cases, it is bouncing out with exactly the same energy, frequency, wavelength, however you call it, than it had when impacting. Now that means that if it has the same frequency, same energy, there is no exchange of energy. This is elastic scattering. And that means that you are getting no information, except that there was a particle there, but you don't get any chemical information because there is no energy exchange. And that is elastic scattering, which is typically called Rayleigh scattering. But you may think that eventually, even if you are using all green photons, eventually some of the photons comes different, red or whatever. That means a change in the color, wavelength, frequency, energy. That means that there has been an exchange of energy, which makes this scattering inelastic. And the nice thing about inelastic scattering is that this photon with a different frequency has some information, can tell you something about the molecule it has impacted with. And that is something that should be like a different kind of radiation. And this is something that actually was not observed experimentally first. But people was wise enough to think, well, this may happen. And people thinking about that was people like Schmeckal, Kramer, Heisenberg, Schrödinger, Dirac, and these names are familiar to you. So that means that people with a very good knowledge about the interaction between matter and radiation were assuming that this is something that could happen. This is something they were assuming. This is something that may theoretically, eventually, occur. Does it occur? Well, yes, we know it does. But who discovered that this was indeed happening? Well, it was Chandrasekhar Venkataraman. And he published that in Nature back in 1928, and 2 years later he got the Nobel Prize Award, essentially because he was giving the first experimental evidence of some kind of radiation that was speculated. And of course he also had a lecture very nicely about the color of the sea, was the title of the lecture, which is interesting, and I will come to that in a moment. And he also says that in the history of science we often find that the study of some natural phenomenon has been the starting point of the development of a new branch of knowledge. And it certainly, he has developed a new branch of knowledge. Raman spectroscopy is currently a very important one, and when you talk with salesmen, expert people from spectroscopy, say, oh yeah, the market share for infrared is growing, it's okay, but Raman market is exponentially growing. So even now, is close to 100 years later, this technique is growing a lot faster than he ever could imagine, because of course technology is enabling that. Now, this is the Raman spectrum of ethanol, which you can find in a wine, alcohol, or any other drink. And there is an anecdote, I can tell you it's not true, but like they say in Italian, si non è vero è ben trovato. If it is not true, it's well told, because it's about, during the ceremony, the king of Sweden was asking Raman to make a toast, but he didn't drink. And then very kindly, he declined, telling to the king, Your Majesty, you have seen Raman effect on ethanol, but I don't think you will be happy to see ethanol effect on Raman. This is not true because at that moment the radiation was not called Raman effect, it was called secondary radiation. It was only a few years later. But this is not true, but it's a good anecdote to tell, and then people will smile and say, well, it's not, but it was kind of a good point to comment. The beginning of that story started long ago. Actually, Raman was going to a conference in Europe on board of a Narkunda, and after going through the Suez Channel, getting into the Mediterranean Sea, for some reason he found that the blue of the Mediterranean Sea was particularly intense, which he liked. And then he started wondering why the sea is so blue, such an intense blue color, which I guess the ocean here is more or less like the Mediterranean, but for whatever climatic conditions, he was shocked by the color there. And that triggered his research, because he was a physics professor in Calcutta, but he was a professor mainly of acoustics. Later on he got into optics. And also interestingly, Raman wanted to go for a PhD in the UK, but they made a medical revision and told him that you are very delicate, London has a terrible contamination, you have a smog, you will die before getting your PhD degree. They didn't give him the grant, fortunately. And because of that, he stayed in Calcutta, he did research, and he discovered the Raman effect. And then he was traveling to Europe, but only for conferences, like in this case. And then he was amazed by why the color of the sea was so blue. And if I ask you why the color of the sea is blue, what will be your answer? Okay, scattering of the light, where? Light of the sun scattering with the of the water or air or. Okay, no, that is the answer, is scattering. But the point is that that was something that had been commented and discussed by many people. And Lord Rayleigh, for instance, he was saying that basically the sea is blue because it reflects the sky. The sky is pale blue, and he said, okay. So what Raman did was something very simple. He looked at the sea through a polarized lens. So what do you get when you are using a polarized lens? You have sunglasses which are polarized.
It vibrates in a particular plane.
Yeah, because they are polarized, there is a reflection plane which is cancelled. So for the sunglasses is very good because sun shines on the floor, and then the lights that come from the floor with a very intense reflection is killed because of the polarization. When you, of course, you do like this, you will see the reflection, but usually you keep the head like that. So this kind of thing is what he did with the polarized lens. He was looking at the sea through the lens. And what he observed is that the color of the sea was even more intense blue than without the polarized lens, which rules out Rayleigh explanation. I mean, it is not blue because it reflects the blue of the sky. It's because of something else which is, so you have a Nobel Prize award. Remember to ask for it after the, because of the scattering of the light with the molecules of the water. And then he started to be, typically in science, there are several kinds of people. And one of these people who see something and say, okay, whatever. And some people who see something interesting. And it appears that Raman said, interesting. And then he wanted to get more information about why scattering of the light was giving that intense blue color. And then he started looking at scattering of light. 1928, like 97 years ago, you were not here. No, I was not here either. But Raman was there. They didn't have lasers, but to work in detail to see what is happening on a sample, and with very specific sensitivity on the colors, you need something. And because you don't have a laser which is red, blue, green, or whatever, he was using the main light source that we all have, the sun. And what he was using is something like this color plastic paper, whatever it is, I don't know the English word for that. Cellophane, maybe English word? Sorry? Maybe, I don't know, but these are like papers that you can see through them. They are very transparent and they can be made of specific colors. So basically the light coming through this paper will only be that color. And he was using different papers, and for instance using the violet paper, basically all the light that was coming to the samples, and he was looking at solid, liquid, all kinds of samples, only violet light was reaching the sample, the rest was filtered. And then he was looking at the sample through other color filters. So basically, when the sample was illuminated with the violet color, if you use a violet filter, you see all the light coming out. If we was using papers of different colors, he didn't see any light coming out, because all the light coming in was violet and all the light going out was violet. But then using different papers, using the green ones, I see a little green light coming. Very weak, but he saw something. And actually you see a very thin line of the green light, because he discovered that even when most of the photons that violet were hitting the sample, they bounce out being violet, a very little fraction was coming out being different, for instance green or yellow or whatever. And that basically was telling you that the sample has taken a little bit of energy from that photon, and when that photon goes out, it has less energy, lower frequency, longer wavelength, different color. So he put that in a paper, he sent it to Nature, it was published, and he got a Nobel Prize award. All the equipment you need is a sun, couple of pieces of papers, and something solid that you can find anywhere. So, but the discovery was fundamental. And you need the intelligence to repair on all these data. And in the end, you have a radiation with a frequency hitting the sample that in most of the time basically goes out exactly with the same frequency. And a little bit comes out with a different frequency. Instead of Hν is Hν prime, which means a different frequency. Now that one is inelastic scattering. And that means that there has been an energy exchange. And then you can get information. Now, filter paper is nice, but you cannot have all collection of filter papers. So in the end, you go to the most paradigmatic instrument in spectroscopy, which is a prism, because with a prism at different wavelengths, the light will be detoured differently. So the higher the energy, the more detoured the light is from red light, yellow, green, blue, violet, and so on. So that is a lot better, because then you can illuminate your sample somewhere over there, collect the light that comes from your sample, and look which light is coming out of your sample. Very little, very weak, I know. And probably looking you won't see anything, but you can put here a photographic film and record it. So essentially this is what he did. So you have a prism in here. This tube is basically looking at the sample which is illuminated by the sun. And over here, basically, you have a photographic film where the light coming from the sample is impinging, inciding. And the way it looks like, basically, this looks like a horn, something like that. Let me go to the... So this is like a horn. So here you have the prism, and then the light goes to it. Typically, he places it 90 degrees, because scattering is, I mean, it goes in every direction, but just imagine when someone is using water flowing against a surface. Most of the water is going to the sides. Typically, if the 90 degrees is where you get most of the scattering. So basically, if the light is coming in this direction, light will scatter in every direction, but preferentially perpendicular. And because of that, he was perpendicular from the sun to the sample, and he was collecting here. And then basically what he was getting here is all the light going through it. And all the light that goes through it in 99.9999% of the time was exactly the color that he selected. If he uses violet light, for instance, 405 nanometer, here you get basically 405 nanometer. But what he observed is that you get additional peaks. Not only one, but probably several, but he got additional peaks. Additional peaks that actually, interestingly, had a different energy, sometimes higher, sometimes lower, but symmetric. I mean, if the frequency increases like 10, then you get minus 10. And if it increases like 20, you get minus 20. Some of them were stronger than the others, but the relative position was always symmetric with respect to the excitation line. And the photographic looks like this. So basically, you get a very strong line, and then the other additional lines. But these are like stronger, and then here you get a very similar one, much weaker at the same positions, but much more weaker. So whatever is happening is like the sample is taking an amount of energy or giving an amount of energy to the photon in the same amount. And it is more likely, when you look here, that actually the energy is taken by the molecule from the photon than vice versa. But sometimes the molecule can give energy to the photon. Do you know why or what that may be? Mainly what is happening is because of this photon, the molecule is going to another vibrational state. And it typically ends in a more excited vibrational state, so it's taking energy. Eventually, some molecule can be in a more excited state, and after this, it gets relaxed. So the photon comes out with more energy. But that is much less likely. That's why even when you get the same peaks, one of them are much weaker than the others. And that's why we typically only look at one side, which is where the photons lose energy, because Raman effect is per se very weak. So if it is very weak, you don't want to go to the less likely effect, but to the most likely effect. So when you make a plot nowadays, it will look like this. So you no longer use a photographic film, but a detector. And then you get the Raman effect here, the elastic scattering here, Rayleigh. And this can have an intensity of 1 to 10 million. The Raman effect will have an intensity of 1. So basically, 1 out of 10 million photons will have the Raman effect. It is an extremely weak phenomenon. And of course, when the molecule gets excited, it is more likely that when the molecule gets relaxed, which is less likely. But these two peaks are completely symmetric, but this one is much more weaker. This one, where the molecule relaxes, corresponds to the anti-Stokes transitions, and when the molecule gets excited is what we call a Stokes transition. But Stokes and anti-Stokes are like the two characteristic peaks of a Raman scattering. Okay, Raman and infrared are connected because the two techniques are looking at transitions between vibrational states. But they look at that, they observe that, they sense that in very different manners. You already know infrared, and you are getting to know Raman. And the major difference is that in infrared, if you remember, we are always talking about infrared absorption. Why? Because you use infrared radiation, and you may only use infrared radiation. it goes through the sample with a given intensity, I sub 0, it comes out with a lower intensity. Why? Because the sample has been absorbing energy from this infrared radiation. What energy has it absorbed? Well, basically energy associated to vibrational transitions. How much energy am I taking? Beer-Lambert law depends on how long is the path, how concentrated is the absorbing substance, and what is the absorption coefficient of these substances. So it's absolutely linear, and you can make very nice quantitative infrared studies. Now we go to Raman. Forget everything about this linear, elegant, simple infrared thing. Now Raman is total chaos. Basically, the photon hits the molecule, boom, it jumps in every single direction. You don't care anymore about what is the absorption of this light with the light. No, you are more interested in the photons that bounce out of the molecule after crashing the molecule. So the first challenge is that photons go out in every direction, most likely at 90 degrees, but in every direction. And the other interesting point on this inelastic scattering, that through the years was called Raman effect, is that you can do it with any wavelength which has at least a minimum amount of energy. What would be the minimum energy that you need to make a Raman effect? Exactly, you need that the energy of the photons will be at least enough to make a vibrational transition. And this at least is infrared. Because infrared is exactly the amount that you need to make these kind of transitions. So infrared will generate Raman effect, and any wavelength with more energy, like visible, be it red, near infrared, red, green, yellow, blue, violet, will do it. And if you go to ultraviolet, it will do it. And if you go to X-ray, you will do it. And actually, you can go to a synchrotron and make Raman scattering of X-rays, which very few people do it, but you can do it. So the nice thing is that you can do that. So basically, to put it in a more graphical way, these are vibrational levels of a given molecule. And at the end of the day, this is what infrared makes. It takes you from a fundamental state, for instance, to the first floor, or from the first to the second, or whatever. It basically takes you to a higher vibrational state. What happens in Raman? Well, in Raman, you have two kinds of phenomena. Okay, so this is also what the physicists like to call a one-photon phenomenon, because it's one photon is taken and you go up, one photon. For Raman, this is two photons, the photon that excites the molecule, which is taken by the molecule, and the photon which comes from the molecule when the molecule relaxes. So these are two photons, and you compare these two photons. Now, what may happen to these two photons? Well, you have three possible scenarios. The first one is like the molecule gets the photon, goes to a virtual excited state, wherever it is, and then the molecule releases the photon and ends up where it was. So basically, the molecule will be on the same level of energy. It will be puzzled, it will say, what happened to me? But it will be at the same level. This is elastic scattering. This is reporting nothing. This is Rayleigh dispersion. But 1 in a million times, something different happens. The molecule gets the photon, gets excited to a virtual state that you don't see, and then it gets relaxed and a photon comes out. But when the molecule relaxes, it relaxes in a higher vibrational level. So the energy coming out from the photon is lower than the energy coming in from the photon. So there is a difference. What is the difference? Well, exactly the same transition. And this is the Stokes inelastic scattering, which is the most likely. Eventually, the photon may hit a molecule which is in a more excited condition. So that means that the molecule will be more or less excited. Photon takes it to the crazy excitement, and then when it relaxes, a photon goes out, but ends up being more relaxed. So the energy of the photon coming out has more energy than the energy of the photon coming in. But if you calculate the difference between this and that photon, or this and that photon is the same, only that one will be positive and the other one will be negative, because it is taking a given amount of energy, or it is given the same amount of energy. And so, I mean, is this clear? Okay. There's one extreme case, resonance Raman, because we are dealing with light. If the sample is absorbing at a given wavelength, like you can tell from ultraviolet visible spectroscopy, and you're using the laser of that wavelength, because the sample is absorbing that wavelength, the absorption of the light increases exponentially. There is a resonance effect. And because there is a resonance effect, the excitement is much more efficient, and then you can trigger the Raman signal exponentially. So the Raman signal will be much, much stronger. With that will be a case of resonance Raman effect. But that happens if you are using a laser of a wavelength that the sample is absorbing. And we will see that later on in any case. So infrared is like when you go to the bus and they only say, no, exact fare. You give me exactly for the transition to get into the bus, or you don't get into the bus. So this is infrared. You have to have the right kind of energy, the right kind of money to do it. But Raman is more versatile, and it will give you change. Like when you go to the coffee machine, the coffee can be 100 economic units. You pay 1,000, it gives you 900. You pay 200, it gives you 100. It will give you the change, but the transaction again will be 100. So this is what happens with Raman. This is a 2 photons you give and you get. In the case of Raman, no, it's exact fair. You give me what I need to do the transition, and that's it. It's a single photon and 2 photon phenomena. This is what the physicists say. And talking about 1 photon or 2 photon phenomena completely changes the nature of what you are observing. Because indeed, you are going from A to B, but you go either directly or you go all the way up and back. So you go from A to B, yes, but the way you use is different. And when you travel, if I travel from here to here directly, or from here to here going like that, I will see different things. Same thing happens for spectroscopy. They will see different things. And what will be the main differences? The selection rules. In a very general, very qualitative, very intuitive manner, the major keys of selection rules is like, okay, both of them are looking at vibrational transitions, that we know. But they have different selection rules. The infrared in general is much more sensitive to vibrations where the dipolar moment, what is the dipolar moment?
Changing charge.
Exactly, you have a like positive negative charge, and if this vibration is moving and this is positive and this is negative, when they move, these exact charges, when they are closer or they are more distant, there is a change in the dipolar moment. Now these kind of vibrations are typically observed by infrared spectroscopy. However, in the case of Raman, it's different. Typically, the stronger Raman vibrations are those where the polarizability of the bond is changing. And what does it mean, the polarizability of the bond is changing? Well, basically, the electrons don't really have a clear preference for one or another atom. They were somewhere in between, evenly distributed. But this molecule will vibrate. When this molecule vibrates, this cloud of electrons will be here like very packed. And then if you apply a field, they can hardly polarize these electron clouds because there is no room for polarization. Everything is already stuck. So you apply a field, they say move, it cannot move. But when the molecules are separated, the same number of electrons are in a bigger space. So they are more distributed. And if you apply the field, zoom, they will move. So you are polarizing that bond when you apply or you do not apply a field. So these kind of vibrations are changing the polarizability. Now these kind of vibrations will be more active in Raman spectroscopy. Is Raman blind to the other ones and vice versa? Not exactly, except in center symmetric molecules. But most of the cases are not center symmetric, so basically vibrations changing polarizability will have a stronger Raman signal and weaker infrared signal, while the other way around, infrared signals will be stronger for where you change the dipole moment, and the Raman will be weaker when you are changing the dipole moment. That means the covalent bonds are mainly bonds that will change polarizability because the electrons don't have particular preference for one element or the other. Like for instance in double bond carbon-carbon or phosphor-sulfur. So if you have the same element or elements with similar electronegativity, that no one is pulling the electrons stronger. Ionic bonds, the electrons tend to go to the more electrophilic side, so that means that it will be more active in infrared. Okay, so this is, for some reason, this is repeated. Okay, and this is the polarizability, so you get a very dense or very dispersed. So here you are changing polarizability, and in this case you are changing the dipole moment. So this is the domain of Raman, and that is the domain of infrared. Preferentially, they share territory. They look at things complementary. And basically here, for instance, you have a dichloroacetophenone, both the infrared on the top and the Raman at the bottom. Some of the peaks will be the same, other peaks will be absent, other will be stronger rather than weaker, and whatever. And you know what is this symbol here? Yes, very good. Why do I put it here? Because of the complementarity. Actually, in Denmark, Niels Bohr, who was one of the fathers of quantum chemistry, the king of Denmark gave him the nobiliary degree. And then you need like a shield of your family. When you are a noble person, you need a shield. And then what Niels Bohr told to the king of Denmark, that my symbol will be that one. And his motto will be contraria sunt complementa, which means contrary things are complementary, which is the yin and yang, because he was fascinated by the philosophy of yin and yang, and how many things that appear to be contrary, they're actually not contrary, but complementary. And for instance, the case of Raman and infrared is a very good example of that. That's why you got this kind of more Eastern symbol within a Western nobiliary family. And this contraria sunt complementa means that sometimes one thing is better than the other, sometimes the other is better than one, and in the end you need both of them if you really want to make a good description of the elephant that you are studying. For instance, in the case of Raman, it typically beats infrared for one fundamental reason, is that any excitation line is good, infrared, near infrared, visible, and so on. And that is very good, because it allows you to work typically with visible and ultraviolet light. And that allows you to see through glass, through quartz, through sapphire. Catalysis is happening with strange gases that you don't want to breathe, at high temperatures, at high pressures, or liquids, or whatever. And you can look through a window and make a Raman spectra in these processes. So that's ideal for in situ and for operando studies. And Raman typically doesn't care about water. Water has a very weak Raman scattering. So if you are looking at very diluted solutions in water, like a very low concentration, you can see the solutes, and the water will hardly give a problem for you. In the case of infrared, has a very strong absorption of water. So you cannot really study that easily water chemistry. You can, but you have to work in the few microns close to the detector. You cannot use absorption infrared, but different things. But Raman doesn't care, can measure without any problem. And that means the water is not a problem, CO2 is not a problem, which are major headaches for infrared. And then if you want to make in situ operando studies in supercritical conditions with water, with CO2, you may do so. Water and CO2 will hardly interfere with your analysis, and you will see all the chemistry happening there. So that's very good. We already said nanocrystals, below 4 nanometers, you can see it, and we have seen it yesterday. Like a tiny amount of a crystal, you see it there, which infrared is not particularly interested or not about that, but that clearly beats mainly X-ray diffraction. And the spatial resolution goes with typically half of the wavelength of the radiation, because you go to visible and ultraviolet, you can be dealing with up to 300 nanometers, which half the wavelength is like 100 plus nanometers. So you can really get into very good spatial resolution. Infrared is using 1000 nanometers. So when you are doing mapping or imaging, that is also another limitation. On the other hand, infrared is better than Raman in several things. It used to be more economic. An infrared system used to be more economic than a Raman system, but Raman systems are becoming increasingly affordable, so that the price difference is becoming less and less important. Spectral resolution is worse in the case of Raman because of the optical, and you will see a drawing later on, but the spectral resolution is lower in Raman, so you win a space resolution and you lose a spatial resolution, and actually there is a common reason, because everything goes in hand with the wavelength, which the wavelength is important for the optical resolution, but the wavelength is also affecting the spectral resolution of the system. So in infrared you talk about 0.1 centimeter to the minus 1, in Raman you will be happy if you say 2 centimeters to the minus 1 resolution. Sample heating with infrared can be a problem because in the case of Raman, a laser is typically used to study the sample, and you might impact too much energy that may damage the sample, may dehydrate the sample, may confuse you, or you are looking at chemisorph molecules and the laser will desorb the molecules. Infrared has not that problem. It will be able to look at those things without major problem. And the main problem of Raman that is not present in infrared is the fluorescence. If you get tiny amount of something which is producing fluorescence, this can kill you because the fluorescence is about 10,000 times more intense than the Raman effect. So even trace amounts of some impurity that is phosphorescence or fluorescence will kill your Raman measurement. There are techniques to go through it, but in general that is the problem. Now, the happening of Raman effect occurs at any wavelength. Here you have the spectral range from, say, UV all the way until the infrared, and basically what happens is, because it's happening at any wavelength, okay, that drawing shouldn't be here, that shouldn't be here, but okay, sometimes slides get scrambled. I cannot blame on anyone because it's probably my fault, so I will not complain and I will just follow, and then I come back to that. This is the resolution against the wavelength. Now, what we observe here is, for a given system, depending on whether you're using a laser of 400, 500, 600, 700, 800 nanometer, you are going from violet, green, red, near infrared, and close to infrared. As you go there, for a given optic, you can change the slit or whatever, doesn't matter, but in general what you see is that the longer the wavelength, the resolution of the spectrum will be better. And typically infrared is occurring here with infrared lights, where you see that there is the better optical resolution for any optical light scattering system that you use to measure the spectra. And in the other side, when you are working with Raman, you are using like near infrared, red, green, violet. So for a given optic, the resolution will be lower. That's why we have a worse spectral resolution in infrared or in Raman. So now the slide that I was expecting to see before. What is typically happening when you get a spectrum of a sample, and we are only going to look at the Stokes, which is where you really get more information than in the anti-Stokes, will be the same but weaker. So basically, this is the laser, UV laser, very intense scattering of it. And then you get Raman signal, for instance, these 1, 2, and 3 peaks, which appear at a given distance from the laser. Of course, this peak is like 10 millions higher than this one, but you imagine that because if I make it to scale, you see nothing down here. But so these peaks appear at a given distance from the laser. You make the same spectrum using a green laser, 514 nanometer, you will get the same peaks with respect to the laser. So they appear at a different position in the absolute spectrum, yes, but the distance of this peak 1, 2, and 3 with respect to the laser is the same that this peak 1, 2, and 3 with respect to that laser. And if you look at the same sample with a near-infrared laser at 788 nanometer, you will get the same 3 peaks, 1, 2, and 3, and these peaks will be at the same distance from the laser. So always the energy taken by these 3 peaks, these 3 transitions, is the same, no matter which laser you use. And if you use an infrared laser, again, you will get the same peaks at the same distance from the laser. One difference that happens, which is important, is that the intensity of the Raman effect will be weaker and weaker as the energy of the photon decreases. So you get very strong Raman effect with ultraviolet, weaker with green, weaker with near infrared, and weaker with infrared. Because the Raman effect increases with the fourth power of the energy of the photon, the fourth power. So basically from here to there, the increase of the Raman effect is dramatic. But the most important thing is that with respect to the laser, the energy that has been taken is the same. That's why we don't show absolute frequencies, but basically we say, with respect to the energy of the laser, where do I get the peaks? And then that is why we don't talk about centimeters to the -1, or we don't talk about wave numbers, we talk about Raman shift. We don't say frequency, we say Raman shift, because it is a shift. It is, we are assuming that the excitation laser is not 3, 4, 5, 600 wave number or whatever, but that it is your reference. And then you make a subtraction. How many centimeters to the -1 have been taken from this laser? And then these peaks will be at 1, 3, and 600 centimeters to the -1 with respect to the laser excitation frequency. You get this point? Because that's fundamental. Sure? Okay, that is important because we are dealing with a difference. So no matter that we are working with high energy photons, we are working with the energy much higher than the vibrational frequency, because in the end what we are looking is the energy taken by the sample. And this is what the Raman spectrum represents, the energy taken by the sample presented in centimeters to the -1. And that's why we don't call it frequency, but Raman shift, because it is not an absolute frequency, it's a different frequency. And this big thing in the middle of the spectrum is fluorescence. When the sample has fluorescence, you have a problem, particularly when you are working in the visible region, because fluorescence is something that we typically see, something that happens in the visible region. So if you have a sample with fluorescence and you are using visible lasers like green or red, the fluorescence will be a problem. And it will be a very important problem. Remember, 10,000 times stronger than the Raman effect. So how do you go around fluorescence? Well, if you use infrared laser or near infrared, the fluorescence will be irrelevant or very weak. So you can see your peaks despite of the fluorescence. Or you may go boldly where nobody has gone before. Say, okay, no, I want to use ultraviolet light. If you use ultraviolet light, the fluorescence will be huge, terrible, but doesn't matter. I'm looking to this laser and the Raman peaks are here, not there. So even if there is a very big fluorescence, it doesn't matter because you're not looking there. You're looking in this region. So even if there is a very, very intense fluorescence there, it doesn't matter because you're looking here. But a Raman system of UVBs is much more expensive because all the optic has to be made of quartz. You cannot make glass. And also the Raman spectra will be affected by the temperature of your sample. This is kind of a thermometer that you can find on the NASA website, which is nice because it tells you the black body radiation very graphically. At what temperature, which radiation emits a body at a given temperature. For instance, we are starting with the Raman that uses infrared radiation, which is typically called FT Raman. Okay, that means that if you are using infrared laser and the sample is emitting infrared radiation, you may have a problem because the Raman effect is very weak. And if you use a Raman infrared, the photons that are coming out with Raman signal will be photons with the energy of this infrared laser and a little bit less. So they will be infrared. But if the sample is hot, it will be emitting infrared. Sample at 100 degrees, you already know that the sample is hot at 100 degrees before you touch it. Because when you get near, oh, heat is coming from here. So you are feeling the heat. Now imagine that you are not a person. Imagine that you are a Raman spectrometer, your detector, and you're looking there, and you see all this infrared coming out. You will not be able to see a few Raman photons because you have millions of photons emitting infrared. It's impossible to see that. So you cannot look at a sample which is at 100 degrees with a Raman that uses an infrared laser. Now, if your sample were at the temperature like 300-400 degrees C, over there it will be emitting near infrared radiation. So a laser that works in near infrared laser won't be able to see anything because you get just overwhelmed by the near infrared radiation. Now, if things get very hot, have you seen in the television news when they are talking, for instance, of a steel factory with all the molten steel? What is the color of it? Bright red. You see like light coming out of it. You see this light. So imagine that you are an spectrometer and you are looking there trying to see some green, yellow photons, and then everything is bright. You cannot see. And the same thing with ultraviolet. If some sample were at 10,000 degrees or several thousand degrees, it will be emitting ultraviolet light, like the sun. The sun, the outermost layer of the sun, is the coldest one. It's only like a few thousand degrees. But this is emitting UV light, and that's why we get some sunburn. But that means that if you're trying to make a spectrum with a UV laser and your sample is at 10,000 degrees, you will have a problem measured. Well, actually, you will not have sample, you will not have laboratory, you will not have Raman, because a sample at 10,000 degrees in laboratory is not doable. But if you could have a sample at 10,000 degrees, even with a UV Raman, you should be unable to see those things. So, very qualitatively, if you use infrared laser and the sample is at about 100 degrees, forget it. The light coming from the sample will make it impossible to see Raman spectra. So, okay, I use a near-infrared laser, okay. But if your 100 is about 300 plus degrees centigrade, near-infrared radiation will be coming out of your sample and you won't be able to see. Of course, you can look at those with a visible and ultraviolet light. If you go to 800 and above, the sample will be bright red. It will be emitting light. It will be white, brilliant white. You cannot measure. And if the sample were at thousands of degrees, even with the UV light, you will have a problem. This is something common. I mean, if you look at the sky at night, you see, for instance, Andromeda galaxy, which is in this image. What you see there is only the coldest part of the stars, the outermost layer, which is only like a few thousand degrees. Nothing, well, compared with if you go out to the street now. But okay. Now, that going back to the laboratory can be a problem. This is an operando reactor. We are making our reaction. Here you have the gas feed. Gas comes from here. This is a thermocouple that goes all the way into the bed. This is the gas outlet. And here we are measuring with a laser. Which color is this laser? Can you see the color? Green. Okay, it's visible light. Now imagine that this sample is at 1, 2, 3, 4, 500 degrees centigrade. Do we have a problem? No. Don't touch it because you will get burned, but for the Raman it will be okay. Now, if you go to 700 or 800 degrees, what happens? How does the sample look like? Bright red. Now you have a problem. When it is not too bright, you can still see something if you are dealing with strong Raman bands. But if you are dealing with weak, that's a problem. But already these bands have to compete with the background light which is coming out. And when it goes more than 800, forget it. You cannot see anything because it is emitting its own light. And it is emitting its own light in a very intense manner and a lot more than what you get from the Raman effect. So you don't see anything. So just to keep an eye on these details, this is what you get from few thousand degrees. Of course, the galaxy is not that gentle. You will also see things that emit X-ray, and these are things at 1,000,000 degrees, but these are black holes. Okay, I just wanted to, because I was using this NASA thermometer, I wanted to go to space, but these black holes are not only in Andromeda galaxy, it's also in our galaxy. Okay, back home, coming from the space. Do we have any problem in Raman coming from space, apart from Andromeda or black holes and things like that? Yes, we have something that came from space, and these are the cosmic rays. Do you know what is a cosmic ray?
More energy. It has more energy than cosmic.
It's like, well, basically, yeah, typically they are nuclei, protons and neutrons coming into the atmosphere continuously. They are typically consequence of explosions of supernovas and whatever. We are continuously getting those things every day. Right now, through this room, a lot of cosmic rays are passing through, which is okay, don't worry. And if they go through your detector, which is a CCD detector that you have connected to your Raman system and you are measuring, and a cosmic ray goes through the CCD detector, it creates a spike. So when you're making the spectrum, this thing that came from outer space will interfere, and in your spectrum you will get a spike, cosmic ray. And usually they happen to be, I mean, they could be in the middle of nowhere, but for some reason they like to appear close to the peak maxima and things like that to make life more complex. And this is something that came from the space, and is happening continuously. Well, actually, cosmic ray, actually this drawing is illustrating something which is very important for the climate of Earth. In addition of what I said the first day about CO2 coming in and out, the climate of Earth is strongly affected by the cosmic rays. The more cosmic rays come into our atmosphere, the more condensation it generates about aerosols produced. That triggers condensation of clouds, triggers rain. And because of these cosmic rays, when we get many cosmic rays, the climate cools down. But in the absence of the cosmic rays, the climate goes up. And through the years, we have had, even in the last 2,000 years, which is more documented, you can see cycles where there was more and less incidence of cosmic rays. How do we know that we have cosmic rays coming into it? I mean, I'm getting away from spectroscopy, but we are approaching the end, and maybe this is a good moment to talk about something different, but relevant anyhow to it. How do we know the amount of cosmic rays coming into our atmosphere, not now that we have electronic systems, but 1,000, 2,000, 3,000, 10,000 years ago, we can tell easily. Okay, you remember when in school they were telling you they study these things from the pharaohs or these things from wherever, and that they do carbon-14 labeling to tell the age of the bodies? How does it work? Who can tell me what is this carbon-14 dating? Hmm? The decay. Okay. But the decay will happen to everything. So why the decay of this dead body is telling you something?
The carbon number.
The balance between carbon-12 and carbon-14 stops after the living being dies.
Exactly. And why does it stop?
Because the C12 and C14 ratio is constant throughout the universe.
And why is it constantly growing?
Means after the dead body and after the body, the living dies.
Yes.
The C12 doesn't get intact.
Yes, but how do we get new carbon-14?
The radioactivity that
The carbon-14 is being generated by cosmic rays. We have protons and you have neutrons continuously coming into the atmosphere, giving spikes into your Raman spectrometers, but they react with oxygen and with carbon and with nitrogen in the atmosphere, triggering a small reaction, like sometimes basically it enriches carbon-12 to carbon-14, and then you get carbon-14 which is continuously generated. And you can tell that, and from that you can do the dating of aging of people. But the amount of carbon-14 is not always the same. Fortunately, we have trees, and every year a tree gets a new layer. Then you can use these layers of the trees to see through the years if there were max higher or lower amount of carbon-14. And then when you make the dating of a given sample, you have to bear in mind that not everything died with the same amount of carbon-14 in the atmosphere. And all these things is helping us mimic what is happening, and all this fluctuation of carbon-14 correlates with changes, for instance, solar activity. When you have a stronger solar activity, this deviates cosmic rays, we get lower cosmic rays, we have hot weather, more hot weather, not because of the higher sunshine, but because the sun is throwing away the cosmic rays, and we have lower condensation and lower rain, or vice versa. When you have less activity, happens the other way around. Or also, when there are changes, like 40,000 years ago, there was a change in the magnetic field of the Earth. The magnetic field is also deflecting those things. So all these things show up. And carbon-14 is a product of it. Beryllium-16, I believe, is another isotope of it, which also report that. The production of beryllium is nice because the decay time of beryllium is 1 million years. So it can tell you paleoclimatology associated to this. Okay, these are things coming from space. Now we are back on Earth, and I always found that this is interesting because in the end everything connects with everything. And so, well, going back to the Earth, Raman is also very good for Earth sciences, to minerals, calcite, whatever, and it is also good in space research. You remember that some time ago they sent a module to Mars with a Raman spectrometer? Many years ago. You were very young. Have you seen any Raman spectrum from Martian samples? No. Because this was a joint international collaboration between Europe and the US, and actually a colleague from Spain, Fernando Rull, was in charge of making this Raman system. But because of this great collaboration between Europe and the US, the landing parameters were calculated in kilometers per hour and miles per hour, and people didn't know that the other one was using a different unit, so the landing that was supposed to be like this was like this. So the Raman spectrometer is totally broken all over the surface of Mars. And someday we will have a Raman spectrometer in Mars that doesn't crash, and we will get, because this is ideal to identify many minerals and many rocks. And okay, so we've been traveling through space, we can tell about other things that we will do tomorrow. So we complete what the Raman is like, and then we will go into catalysis again. how can we cancel the fluorescence? Okay, that's a very good question. There are several ways. And typically, fluorescence may have different origins. Sometimes it's a composition origin. Like for instance, an alumina, they have a tiny amount of chromium atoms within the alumina lattice. And those generate a fluorescence. So there's some aluminas that will always produce fluorescence no matter what you do. And this, you cannot get rid of the fluorescence. Because one thing is to say, try to get rid of the fluorescence in this sample with a visible light laser, which is the ones most of us have. In other cases, the problem of fluorescence is because of environmental junk. Micro nanoplastics are all over there. Many of them are polyaromatics. Many of them go to the surface of your material. And if you are dealing with catalysis, catalysts have high surface area, 100, 200 square meters per gram. That means that they can absorb a lot. And then you're going to take a Raman spectrum, fluorescence. So, how does a spectrum with fluorescence looks like? Well, basically, if your sample has peaks like this, if you have fluorescence, the spectrum will look like that. And you don't even see that. So how do you handle that? Okay, with high surface area materials, what you do, if they can take it, is that you treat them at 400 or 500 degrees C. And typically these are catalysts that have been synthesized and calcined at 400 or 500 degrees C. So you can put it in the oven for 1 hour at 500 degrees C, quickly go to the Raman, take a spectrum, and then the sample will be clean, and you can take Raman spectrum of that sample, because you have burned away all the environmental polyaromatic rest of plastics which exist in the air. So that is helping in very many samples. In other samples, sometimes it is because of interesting things. Sometimes you want to make a dehydrated sample and it's fluorescent. An ambient sample is not fluorescent, because sometimes with the hydroxyl groups you get phenomena that trigger fluorescence. So you dehydrate, and then all of a sudden you get some kind of interaction that produces fluorescence. But the way is fighting with burning it away if you can. The other option is you go to different wavelengths and you avoid it. But now, because systems are becoming faster and faster, more and more sensitive, there are companies, for instance, there is a company in Finland which is called TimeGate, which has started making very nice Raman system. It is called TimeGate because it's basically pulsing the laser. Why? Because a Raman phenomenon is very fast. So if this is time 0, and at time 0 you put the laser, a photon goes, immediately you get the Raman peak. And then fluorescence takes a little bit more of time and goes there. But you have this window of time from the photon goes till you get the Raman, and then the fluorescence starts to grow. We're talking about picoseconds, which is very little. Now, how do they work? Well, this Raman system is working with very fast pulses of the laser, very fast reading and closing the shutter. So basically, you through the laser, look at measure, close the eyes very rapidly, then the fluorescence come out, throw the laser again, you look at it, close your eyes very quickly, so, and you make that very many times. In 1 second, you make it thousands of times. So what happens? That, I mean, one spectrum will look like very, very noisy. You can hardly know what you have there, but because you're doing it in 1 second 1,000 times, even with you have a very low signal to noise ratio, at the end of the day, you will have it like this, and that will be totally ignored because you are only looking when this is coming out and before that one comes out. You do it many times. Those systems are becoming increasingly affordable. Spectral resolution is not very good, but it's a very elegant, very smart approach, which is helping you looking at almost any sample without being worried about the fluorescence problem. The other option is that you go to UV laser, which is here, so the fluorescence will be huge, but doesn't matter. Your laser is here and your Raman peaks are here. So even if the UV will make a lot stronger fluorescence, doesn't matter, you're working here. But the fluorescence, but the use of the UV light has a danger. Your samples typically absorb UVBs. So when one sample is absorbing UVBs, typically you will see something like that. And maybe at 200 or 300 nanometer, your sample is absorbing something. So when you work with visible light, you work here. Okay. When you work with ultraviolet light, you work here. 325, for instance. So what happens? That whatever is absorbing here from your sample will be resonantly enhanced. And the spectrum will be dominated by this part of the sample. Imagine that this part of the sample is 5% of the sample. So you get a beautiful spectrum of an anecdotic part of the sample. And then you make all your story about something that may not be representative. That's why when you go to the ultraviolet, it is very important to be aware of this. Some materials are absorbing also in the visible region, like partially reduced oxides absorb at about 600, okay. But usually, in most of the cases, the main problem about resonance confusion is there, because maybe you're doing that and you're not aware. And sometimes you see paper, oh, I use UV Raman, I get rid of fluorescence and I see that. I agree, but that's not all the story. You are being fooled, because by doing that you get rid of the fluorescence, but you must be aware of that. And you must be aware if all your sample is like this or only 1% of your sample is like this, because the spectrum will be dominated because of the resonance enhancement of this part. So fighting with fluorescence is still quite an ongoing challenge, but that's why it's very important always to be aware of your sample and what is the absorption lines of your sample. Because you may have this, you can use it if you know, but you can be fooled if you don't know. Questions, comments, suggestions? Okay.
So you mentioned the cosmic rays. The
Yes.
spikes are coming due to the cosmic rays.
Mm-hmm. Yeah, they came from space.
So, but you are doing in the confined environment by using the laser. So how the cosmic rays enter into this spectrum?
Well, the cosmic rays go through this room, go through this planet.
But
You cannot really shield it. But you're dealing with nuclei. You're dealing with naked protons and neutrons which go down there. If they interact with the nuclei, they trigger a nuclear transition, and it can create. Well, actually, the chemistry in the atmosphere is very nice. I don't remember now, but depending whether this is proton or neutron, is creating many things like carbon-14, like beryllium, like multiple isotopes. But usually, most of it will go through you, it will go through me, it will go through this table, it will go through a shielding without major problem, because most of the matter is not solid as we think. Remember all the experiments where they were throwing alpha particles through the material, they just go through it. This is empty even when it appears solid. 99% is orbitals and energy, but no matter. So they go through anything, and they go through the detector, and then you get the spikes. And you cannot really screen that, except if you have a very strong magnetic field in your planet, or if you have a solar activity with very strong solar wind, which is diverting these gases, these cosmic rays somewhere else. But if they are coming, you cannot stop them or anything. They will just go through you, through me, through everywhere. And that's why we have a higher amount of carbon-14 than our ancestors. And then there will be one day that our carbon-14 will decrease, but that will be a bad signal. That means that we are already dead. Okay?
I have one question on fluorescence.
Yes.
So sometimes in some of the samples, if I just load it at room temperature, I take visible laser spectrum 532 nanometer, for example. I have a clean spectrum. I take it to 200, 300 degrees Celsius. Now I have issues with fluorescence.
Hydroxyls typically do this kind of thing. Sometimes hydration quenches some surface phenomena associated to that. And sometimes with zeolites, that's a problem, because you see quite a nice spectrum of the zeolite, then you hit to dehydrate, and then all of a sudden you get fluorescence coming out.
That means if I have a complete monolayer coverage, the chances of fluorescence are going to go down if it is coming from the
It should go down, because I don't really know the nature of it, because something that I found somewhere is not that much studied, but that's actually quite an issue. Because usually you wouldn't expect that. You get a nice ambient thing, and ambient things means hydrated, and then you heat and you get that.
Yeah, because that's what my experience with some moly on alumina.
Mm-hmm.
With increasing loading, with the low loading, I go to higher temperature, I see fluorescence. With full monolayer coverage, I go to higher temperature. Fluorescence is quite a bit suppressed.
Exactly. So that goes in hand with this.
Yeah.
Or even alkali doping that will also strongly bind to hydroxyls or whatever. Yeah, these kind of things will be. But this is actually a very good example that illustrates that. Like for a given sample, little by little, you are minimizing the surface hydroxyls, and then you avoid this problem on dehydration.
So, is there any role of the
A rule by using the band gap, you say, for?
Band, so every material has their own band gap, right?
Yeah.
So by choosing the lasers,
Mhm.
so do we need to take care of the band gap of the material also to get a good spectrum?
Okay, the band gap is basically an extrapolation more or less of when you are starting to absorb. So over here, that will be the band gap of this material, which will be a given wavelength, whatever, and then you say that this is like 3 electron volts. But in the region of the band gap, usually you don't have any significant absorption. So a laser at that wavelength shouldn't be a problem. The problem for the resonance is that you are using a laser here or here. And the spectrum may look very different if you look with this than with that laser. Because in this case, you are going into the resonance effect. Or sometimes even something happens near resonance. If you do it over here, you get some resonance, not absolutely, but you enhance a little bit, and then the photons come out here at this wavelength, and they come out nicely. But if you use a laser here, okay, you don't get a big resonance, but then the Raman photons will come like this, and they will be absorbed by the sample. So sometimes it's...
So if I choose the laser which has the more energy than the 3 eV,
like this one.
more than 3 eV, that side.
Over here.
Over here, that side.
But in this region,
Then you will have the electronic transition, right?
well, I mean, you will have a little bit of better absorption, but it's not like the resonance, it's not like the key absorption. But it will increase a little bit, and the photons will still go out because the absorption of the sample is lower. Because you have your sample, you get the photons, and then the electrons go out. And if this sample is absorbing a lot, this may attenuate. But usually this is very unlikely. Typically, you are really free, far from resonance, like here or there. You are far from resonance, or you are in the resonance region, and then you have this near resonance, which can be a little bit more confusing. But typically, you are far from resonance or in the middle of resonance. But that's why this is important to use the right excitation line, to know, basically, to know this. But this very most often usually is below 300 when you really get absorption of most of the transition elements. And over here you will only get like DD transition from reduced elements.
Okay, electronic transition.
But that can be good because, for instance, there is one example I will show you tomorrow or after tomorrow about partially reduced molybdenum oxide, like molybdenum 5 within molybdenum 6. This one is absorbing at about 600 more or less nanometer, which is the red laser 633. So you are looking at this mixed oxide with the green laser, which is okay. The spectrum will be like that. It absorbs at about 633, 600 more or less. So you use the 633 laser, and then this partially reduced molybdenum show nicely in the spectrum. But you typically work with the green laser 500 over here. And this sample with partially reduced molybdenum has very weak Raman signal, so you get a very poor Raman signal. And so it looks like whatever. But when you are using this laser, because you are getting there, you get clear bands associated with this partially reduced molybdenum, because you are resonantly. So it can be misleading, but when you know it, you can use it. That was a very elegant work made by Gerhard Mestel and Helmut Knetzinger in Germany. About mixed molybdenum oxides, and it was very interesting, taking advantage of these things. But this is not for the first year degree, this is for a senior expert, but this is a very interesting.
Thank you very much.
My pleasure.
Okay, so there are questions from the online participants.
Okay.
So they told a beautiful explanation by Professor.
Thank you.
And the next, there is one more question. What is DRSPL and how it's different from UV spectroscopy?
Wait, what is?
DRS,
Diffuse reflectance.
diffuse reflectance PL. PL
Photoluminescence.
photoluminescence.
PL, photoluminescence, and
How it's different from UV spectroscopy?
well, that's the okay. In UV spectroscopy, basically you are absorbing a radiation. So you are using like a different wavelengths, and then you are measuring like I don't know here. If you are going from 200 to 700 nanometer. So I'm left-handed, that's why it looks awful. So basically you are using the light going through the sample, and then you are recording how much is being absorbed. In the case of photoluminescence, you are irradiating the sample, with a given wavelength, I irradiate the sample with 300 nanometer light, a UV light, and then you measure the light that is emitted by the sample. And then maybe you are exciting at 200, and then you are emitting at like 600 and 630 nanometer. And this photoluminescence will tell you about the element you have, the oxidation state it has, the environment it has, and it will depend on the excitation compared to that. But that's different. In the UV-Vis absorption, you are looking at absorption associated with ligand to metal charge transfer, with the DD electron, but this is electronic information about where they are absorbing energy characteristic of these transitions. And over here is light emitted as a response to an excitation. So somehow that will be like a two-photon phenomenon. You excite and you observe the emission. And in this case, basically it's a one photon. You go through it and it is taken.
Following that, there is two more questions.
Okay.
So they would like to know what is the Kubelka-Munck function.
The Kubelka-Munck function. Okay, but this is typically used for diffuse reflectance spectroscopy to measure the intensity, because when you are doing diffuse reflectance spectroscopy, okay, for typical UV-Vis, you are going through the sample, you measure, so this is Beer-Lambert, it's very easy. You basically the path, the concentration, and the absorption coefficient, you measure everything. But for diffuse reflectance, you get the radiation going to the sample, and then all the light goes out in all directions, and then you get mirrors that concentrates everything, and finally goes to a mirror that goes to a detector. And what Kubelka-Munck-Schuster, KMS, function is doing, or Kubelka-Munck, is basically calculating a way to represent the intensity that you are getting here, because if you measure it, you get an intensity, but that intensity is apparent. And the Kubelka-Munck is basically considering that light is being scattered, collecting in very many angles and very many directions, and it is making a correction, it's getting like maybe a better defined profile based on that. But the Kubelka-Munck is basically a way of treating this data, the intensity against the wavelength that you are observing here, and that the idea is by doing that, by considering all this scattering, this will be more quantitative than that.
Okay. And how it is helpful for band gap determination?
The scale for?
How it is helpful to determine the band gap?
Is energy.
The gamma, why is it useful?
No. How it is useful to find out the band gap?
A way to calculate the band gap?
Yes. How is it used to calculate the energy?
Okay, well, yes, I made here just a drawing extrapolating like you do like that, but usually you have an equation to calculate that from this region to get into this. I don't remember now exactly how it is, but that can be easily found. But there is a way to calculate the gap energy. Actually, there was a paper made by Xingtao Gao and Israel Wax, about a very good method to calculate that. I can look for it and hopefully, and then I can share tomorrow. But that was a very nice method, and actually when we are doing something, this is the kind of equation that we are using to calculate that. Because this really helps you a lot to tell the size domains and nuclearity, whether you have a more polymeric or oligomeric units within a large solid material.
So there is another question from Suraj. He's asking, can we use the Kubelka-Munck function in drifts for quantification?
It's more quantitative than the other one. It's not absolutely quantitative, it is assuming many things, but I mean, if you want to be quantitative, you have to go transmission for infrared or for Raman. For infrared or for UV-Vis. Kubelka-Munck is the best approach that you can do with all these scattering radiations. Okay, and I guess that this is time.